So we talked about the rate of a reaction. The rate law shows us the relationship between the reaction rate and the concentration of the reactants. So here the rate is equal to some constant K, call that the rate constant, times the concentration of A, the reactant. Here we're looking at a very simple decomposition reaction. We have one reactant and it's disappearing, it's decomposing into products. So we're going to look at the rate as a function of this concentration, and that's raised to a power of N. N is what we call the reaction order. That order may be 1, it may be 0, it could be 0.5. You can have fractions even. So if the reaction order is 0, N equals 0, and then what happens to the rate? What's A to the 0 power? 1. So then the rate equals the rate constant, and it's actually independent of the concentration of A. The rate is just the same all the time. If we have a first order reaction, N equals 1, then the rate is going to be directly proportional to the concentration. Second order, the rate will be proportional to the square of the concentration. So let's look at some graphs. So here we're looking at reactant concentration versus time. So the concentration of A as a function of time. For all of these reactions, that concentration goes down. For the 0 order, we see that it goes down in a linear fashion. It's a straight line. The slope of this line is the rate. So the rate isn't changing, it's constant. For a first order reaction, there's more of a curve, and we see that the slope of the line is decreasing as time goes on. And here, for second order, there's even more curvature. If we look at rate versus reactant concentration, for a 0 order reaction, the rate is the same. Doesn't matter what the concentration of A is. First order, the rate is directly proportional to the reactant concentration. As A goes up, the rate goes up. There's this really disturbing lag in my pointer. And for the second order, it goes up more steeply. So how can you have a reaction that is not, where the rate is completely independent of the concentration of the reactant? Yeah, question? For the second order, it's proportional to the square of the concentration. Concentration squared. This is an example of a 0 order reaction. Here we have the sublimation of something. Sublimation, remember, is the transition between a solid directly into the gas state without melting. The rate of this sublimation occurring really only depends on how many particles are on the surface of this substance. Right? The more particles on the surface, the faster the sublimation occurs. But as one layer of atoms sublimates, another layer of atoms underneath is there right away. So essentially, the area of this is not changing, at least within a reasonable period of time. And so the rate of the sublimation does not depend on the concentration. So we see these sorts of reactions when the amount of reactant available for reaction is unaffected by changes in the overall amount of the reactant. So there is no, I forgot what I was going to say. As time goes on and this sublimates, the amount of the reactant that is present here in the solid form is decreasing, but the amount of reactant that's available for the reaction isn't changing. And that's why the rate doesn't change. First order reaction we see is directly proportional to the concentration. As the reaction proceeds, the rate slows down because the concentration of the reactant is decreasing. Second order, proportional to the square of the reactant concentration, so it's even more sensitive to the reaction concentration. How do we figure out what order the reaction is? This can only be figured out by experimentation. You can't predict what the order is by looking at the chemical reaction or anything like that. You actually have to measure the concentrations and the rates and determine it experimentally. One method, question? Mm-hmm. Okay, so the question is about the zero order reaction, because it's a little hard to understand how could the amount available not be changing when the amount of stuff is changing. Right? It's changing states, but does that mean that it's being conserved? No. So let's think of this. Let's just think about the sublimation as occurring on this top layer. So we've got, you could measure, you could count 2, 4, 6, 8. I don't know. Let's say it's a 10 by 10 square, 10 atoms by 10 atoms. So you've got 100 atoms on the top surface, and it's only sublimating from the top, just for simplification. When those 10 times 10 is 100, when those 100 react, are they all gone? No. What's underneath the first layer of 100? Another layer of 100. But eventually they will all sublimate. Eventually, yes. Eventually the zero order reaction will stop when all the reactant is gone. So you can't take this necessarily to an extreme. Because, honestly, this is sublimating from all surfaces that are exposed, right? And so as those layers get peeled off, the area exposed is going to become smaller. And so the rate will go down a little bit. But it's pretty insignificant compared to, say, a first order reaction. Okay? So it's not perfect. Anybody else have any questions about that? So figuring this out, one method is called the method of initial rates. So we just look at the initial rate of the reaction, which is relatively easy to measure, and we do that several different times, changing the concentrations of the reactants. So here again, we're just looking at that simple reaction where we have A decomposing to form some products. So if the concentration of A initially is 0.1 molar, we can measure the initial rate, maybe over the first 10 seconds or whatever, and find that the initial rate is 0.015 molarity per second. Then we can set it up again and start with a concentration here that's twice as much. So the initial concentration is twice as high, and then we measure the rate and we find out that the rate is also twice as high. Oh, okay. What if we double the rate again? Double the concentration from 0.2 to 0.4. The rate doubles again. So we see that this is times 2, and this changes by a factor of 2. We double this again, and this doubles again. The rate is proportional to the concentration. You double the concentration, you double the rate. If you cut the concentration in half, what do you think the rate would do? It would go down by half. What if you triple the concentration? The rate will triple. So this is a first order reaction. The rate is proportional to the concentration. So this is first order. So first order says that the rate is equal to a constant times the concentration of the reactant to the first power. We don't usually write one, so I'm going to leave it out. Everybody okay with that? Next part says determine the rate constant. K is the rate constant. How are we going to find that? Well, if we're going to use this equation, we need a rate and we need a concentration of A. Do we have that information? Yeah, we've got 3 sets of that information. Does it matter which one we use? No, because the rate constant is a constant, right? It stays the same. I'm going to use the first one just because, I don't know, seems reasonable. So we can rearrange our equation there. The rate constant equals the rate divided by the concentration of A. So 0.015 molarity per second divided by the concentration, 0.10 molar. I should be able to do this in my head, but my head's not working very well. 0.15. What are the units on that? Per second. So we could write that as 1/2. We could do it like this, which can be a little confusing, or we can say 0.15 s to the minus 1. So that's the rate constant for this particular reaction under those particular conditions. Questions? Here's an example of my pointer not working. This did this to me in 1A last fall. Doesn't matter where I point, pointer shows up in the same place. So useful not. Okay, look at the 0 order. So the concentration is 0.1, the rate, initial rate is 0.015. Double the concentration of the reactant to 0.2, what happens to the rate? Doesn't change. We double it again, the concentration, what happens to the rate? It's the same. So 0 order, the rate is constant. That's how we recognize a 0 order reaction. For this one, which I can only point in that one particular place, second order, so the initial rate, again, is 0.015 at 0.1 molar of A. We double the concentration. What happens to the rate? Well, we can see what is 0.06 divided by 0.015. So that increased by a factor of 4. So from here to here is times 4. How much did this increase? By what factor? 2. And if we go from here to here, that's another times 2. And what's this relationship? Times 4. So the concentration is changing by a factor of 2. The rate is changing by a factor of 4, which is 2 squared. So that's a second order reaction. So sometimes you can look at them and say, okay, that's all great. Other times you're like, I'm just kind of lost here. What do I do? Isn't there some formula, some equation I could use? I like equations. Yeah, there is. It's this guy down at the bottom. Oh, look at that. It's back. Phew. Great. So you can use this. The rate 2 divided by rate 1 is equal to K times the second concentration to the n power divided by K times the concentration in the first one to the n power. So let's do this for that second order reaction, because the equation is not super obvious, is it? So I'm going to use this as 2, and so this will be rate 1, this will be rate 2. So I'm going to take rate 2 was 0.060 and divide by rate 1, 0.015. That should equal the rate constant times the concentration. For this second one, it's 0.2, and that's raised to the n power, divided by the rate constant times the concentration, raised to the n power. We don't know what the rate constant is. We don't know what the order of the reaction is. What happens to the rate constant? It cancels out. Nice. Well, we know that 0.06 divided by 0.015, we did the math for there before, that equals 4. So that equals 0.2 to the n divided by 0.1 to the n. Which is the same as 0.2 over 0.1, the quantity to the n. I ran out of space. So 0.2 divided by 0.1 is 2 to the n. This one we can just look at and say, oh, well, n must be 2. Any questions? Yeah, if you can't see it, you can use logarithms. So let me show you how that works over here. 4 equals 2 to the n. If I take the log of both sides, base 10 log. So the log of 4 then equals the log of this thing. But when you do something like this is equal to the exponent times the log of that number. 2 log n. I'm sorry, n log 2. I read it backwards. So then n must equal the log of 4 divided by the log of 2. And you can do that a couple of different ways, but it does come out to be 2. Any questions?
So that's an alternative to the first one, right? Or is that...
Yes, this using this rate 2 over rate 1 is an alternative to looking at the concentrations and how the rate changes when the concentration changes.
I just mean in terms of the laws.
Oh, yeah, using this is an alternative to just looking at that and saying, oh, I know what that's supposed to be. Because if the exponent isn't an integer, it can get pretty tricky. Yeah. And so that's when you need to do the logs. Like, we'll see one that has an order of 0.5. You should know how to do it, yeah. Any other questions? Let's look at what are the units for the rate constants for different orders of reactions. And my mind just went blank.